So number 26. Let me move this over a little bit and get this more centered. Alright, so it says in number 26, the diagram below shows a small shaded square inside a larger square. Small shaded square, larger square. Small square is 10 inches on one side, large square is 20 inches on one side. So a point is located at random inside the larger square. Based on the dimensions in the diagram, what is the probability that the point will be inside the small shaded square? So you throw a random point, and what's the probability that that point will land somewhere in here? Actually, let me get a larger line. Like, throw something random, and what's the probability that a point will happen in there? Well, it equates to finding the probability fraction. If you think about it, this is the formula for the probability fraction. It's the desired outcome divided by the possible outcome, or the ratio of the desired outcome to possible outcomes, or total possible outcomes. Think about it. If you flip a coin, right? Flip a quarter, right? And you call heads or tails, the probability of you getting heads is 1 out of 2 possible choices, right? You want heads, and there's the choices of heads or tails, so it's 1 out of 2. The same rationale applies here. You want to know what's the probability that whatever the random point is, will it land in the shaded square? And that is the same as basically taking the area of this small square and putting it over the area of the entire square, because the entire square includes all possible outcomes, right? So if I find the area of the small square, 10 multiplied by 10, or the side square 10 multiplied by 10, divided by the area of the large square, 20 times 20, or 20 squared. Well, 10 squared is 100. 400 squared is, 20 squared is 400, and that's the area in inches squared, right? Well, that's equal to 1 over 4, right? And that's the probability fraction for landing inside this small shaded square. So if you look out of all your options, choice D would be your option for this one. So let me scroll down a little bit and we'll move on to 27. 27. The graph below shows Danielle's speed in miles per hour during 24 minutes she spent riding her bicycle one day. Which of the following is closest to the number of minutes that Danielle's speed was greater than 14 miles an hour? So if you look at this, the bottom of it is in minutes, right? This is how many minutes she rode, 24, and this up and down represents miles per hour she went. So you're looking for how many minutes, let me underline this, how many minutes Danielle's speed was above 14 miles an hour, or greater than 14 miles an hour. So if you look right about here, this would be 14 miles an hour. Because you think about it, between 0 and 4 is 2, between 4 and 8 is 6, so 14 miles an hour is here. Actually, I have that written out, so I'll just show you that. Here's the 14 mile an hour line. Everything that happens above this line is what we're looking for, and we're looking for how many minutes is she above 14 miles an hour, or greater than 14 miles an hour. Well, I filled in the missing numbers here, because in the original graph there were numbers missing, and it's kind of hard to read when numbers are missing. But when you fill in the numbers, then you can just draw a line in your imagination to where it hits, right? So on her third minute she started going above 14 miles an hour, and then on her 21st minute she started dropping below 14 miles an hour. So the time in minutes that she went over 14 miles an hour is 21 minus 3, because here's the speed line where she drops below. So if you take 21 and subtract 3, you're left with 18, right? 18 minutes. So for 18 minutes, Danielle traveled above 14 miles an hour. And if you look, right here, choice C is that. So moving on to 28. Now 28 is kind of interesting too. A mechanic has 2 pieces of sandpaper of different sizes. Each piece is in the shape of a circle. The radius of the larger circle is 4 times the radius of the smaller circle. The area of the larger circle is how many times the area of the smaller circle. Now I know the temptation here is to put, well, the radius is multiplied by 4 or times by 4, so the entire area should be times by 4. But the mathematic tells us that our intuition is wrong here. If you look in the back page of your Mcas, or the formula sheet of the Mcas, they give you this equation, right? The area of a circle. Area equals pi times the radius squared. So the radius of the larger circle now is going to be 4 times r, right? The radius of the larger circle is 4 times the radius of the smaller circle. So considering this as the formula for the area of the smaller circle, then the area of the larger circle becomes this. The area equals pi times 4 times the radius squared. This entire thing is squared. Do you see that? Take a look at it. Alright? And when you take this entire thing and square it, you have to square the coefficient, or you have to square the number in front of the r, right? So 4 squared, that's 16, and you kind of like distribute this exponent across the 4 and the r. So 4 squared is 16, and r squared is just r squared. And doing a little rearranging here, using the commutative property of multiplication, the area of the large square is 16 times. And if you look at this and look at the area of the small square, hey, they're the same. So it's 16 times the area of the smaller circle. And that would be your answer. You would look for the answer 16, and that's that. Or actually, let me even show you it, because it's in here somewhere. 16. Yeah, it's hard to work with Adobe PDF files. It would be choice D, 16.